When you type google.com into a browser, your computer doesn't know where Google is. It knows an IP address like 142.250.191.46 is the actual address of a server. DNS is the system that translates human-readable domain names into IP addresses. Without DNS, you'd have to memorize IP addresses for every website. You'd have to tell your users visit 165.22.58.101 instead of visit emyap.com. And if you ever moved your server to a new IP, you'd have to tell every user to update their bookmarks. DNS solves all of this. The domain name stays constant. Under the hood, you update a DNS record to point to the new IP. Users visit emyap.com, their computers automatically find the new IP, and they don't even know anything changed. Understanding DNS is not optional for deployment. Every web application needs it. When you configure a custom domain, when you set up HTTPS certificates, when you verify your domain for email services, all of it requires understanding DNS records and how they work. The core mental model, DNS is a global, distributed database. The key is global and distributed, there is no single DNS server. The database is replicated across thousands of servers around the world. When you change a DNS record, it propagates across this global network over a period of time, which is why DNS changes aren't instant. Let's trace what happens when you type emyap.com in a browser. Understanding this flow makes every other DNS concept easier to understand. Step 1. Local cache. Your computer first checks its own DNS cache. If you visited emyap.com recently, the IP address is stored locally. No network request needed. The cached entry has a TTL, time to live, that determines how long it's valid. Step 2. OS resolver. If not cached, your operating system asks its configured DNS resolver, usually your router or your ISP's DNS server. Step 3. Recursive resolver. Your ISP's DNS server is a recursive resolver. It does the work of finding the answer. It checks its own cache first. If not cached, it starts the full resolution process. Step 4. Root nameservers. The recursive resolver asks one of the 13 root nameserver clusters. Who knows about .com domains? The root server responds with the IP addresses of the .com TLD, top-level domain, nameservers. Step 5. TLD nameservers. The recursive resolver asks a .com nameserver. Who knows about emyap.com? The TLD server responds with the authoritative nameserver for emyap.com. This is your domain registrar or DNS provider's nameserver. Step 6. Authoritative nameserver. The recursive resolver asks the authoritative nameserver for emyap.com. What is the IP address of emyap.com? The authoritative server responds with your record, the IP address of your server. Step 7. Response. The recursive resolver caches the answer, for TTL seconds, and returns it to your browser. Your browser connects to the IP address. This entire process typically takes 50 to 200 milliseconds on the first query. DNS has a hierarchy. Understanding who controls what helps you know where to make changes. At the top, your domain registrar. GoDaddy, Namecheap, Google Domains, AWS Route 53. When you buy a domain, you buy it from a registrar. The registrar controls which nameservers are authoritative for your domain. This is the NS record, it points to who holds your actual DNS records. In the middle, nameservers. These are the servers that hold your DNS records. They can be your registrar's nameservers, often the default, or a separate DNS provider like Cloudflare, AWS Route 53, or DigitalOcean. When someone queries DNS for emyap.com, the global DNS system eventually routes them to your nameservers for the definitive answer. At the bottom, DNS records. The actual data, A records, name records, MX records, TXT records. These live on your authoritative nameserver. The typical workflow for a new domain: 1. Buy domain from registrar, e.g., Namecheap. 2. Optionally, point nameservers to Cloudflare for better DNS management. 3. In Cloudflare, or your registrar's DNS panel, add in a record pointing emyap.com to your server's IP. The reason many developers use Cloudflare as their nameserver even with a different registrar: Cloudflare has better tooling, faster propagation, DDoS protection, and a free plan. Understanding this hierarchy prevents confusion. If you update a DNS record and it's not working, check that you're updating it on the right nameserver, the one you've configured as authoritative. DNS isn't just one type of record. It stores several types of records, each serving a different purpose. The A record maps a domain name to an IPv4 address. emyap.com 165.22.58.101. This is the most fundamental DNS record. When you deploy a server and want a domain to point to it, you create an A record. The quad A record maps a domain to an IPv6 address. Same concept as A but for the newer IP format. Not strictly necessary unless you're specifically supporting IPv6. The name record maps a domain to another domain name, not directly to an IP. www.myap.com. When someone visits www.myap.com, DNS looks up myap.com's IP and uses that. Useful for subdomains and for pointing your domain to cloud service hostnames. The MX record, mail exchange, specifies which mail servers handle email for your domain. Required if you want email addresses at your domain, at myap.com. The TXT record stores arbitrary text. Used for domain verification, proving you own the domain to Google, SSL certificate authorities, or email providers. Also used for SPF, DKIM, and MARC email authentication. The NS record specifies which nameservers are authoritative for the domain. Set at the registrar level, not the DNS provider level. If you switch DNS providers, you update the NS records at your registrar. For a basic web application deployment, you primarily need a records to point your domain to your server IP, and TXT records for Let's Encrypt domain verification. Let's walk through the exact steps to set up DNS for a new application deployment. Prerequisite: you have a server with a public IP address. For this example, let's say the IP is 165.22.58.101. You've bought the domain myap.com from a registrar. Step 1: access your DNS provider's control panel. If you're using Cloudflare, add your domain to Cloudflare, then update the nameservers at your registrar to Cloudflare's nameservers. If you're staying with your registrar, log into their DNS management panel. Step 2: create an A record for the root domain. Record type, INAME@, this means the root domain, myap.com itself. Value, 165.22.58.101. TTL, 300, 5 minutes for initial setup, increase to 3600 after things are working. Step 3, create an A record for www. Record type, A in name, www. Value, 165.22.58.101. TTL, 300. This makes www.myap.com work. Alternatively, you can use a name, www.myap.com. Step 4, wait for propagation. New records typically take a few minutes to a few hours. Your TTL setting controls the maximum propagation time. Step 5, verify the records are live. Dig myap.com and dig www.myap.com should show your IP address. If they do, DNS is configured correctly. Jinx configuration that works with this DNS setup, server_name myap.com www.myap.com in your Jinx server block. TTL is the number of seconds that DNS resolvers are allowed to cache your DNS records. It directly controls how quickly your DNS changes propagate globally. Low TTL, 60 to 300 seconds. DNS resolvers discard the cached answer after 60 to 300 seconds and requery the authoritative nameserver. Changes propagate quickly, within minutes. The cost, more queries to your nameserver, slightly more load. High TTL, 3600 to 86,400 seconds. DNS resolvers keep the cached answer for 1 to 24 hours. Changes take that long to propagate. This is appropriate for stable records that rarely change. The benefit: fewer nameserver queries, faster DNS resolution for end users. Best practice TTL strategy: before you plan to make a DNS change, like migrating servers, lower your TTL to 60 seconds 24 to 48 hours in advance. This lets existing caches expire quickly. Make your DNS change. After everything is working, raise TTL back to 3600 or higher. If you change the DNS without lowering TTL first, some users might get cached old IP addresses for hours. If your old server is down, they can't reach your site even though DNS is updated. Their DNS resolver is serving the cached old answer. TTL doesn't guarantee propagation time, it's the maximum time a resolver will cache before requerying. Actual propagation can be faster because resolvers may not have cached the old record. But TTL is the worst case time. For new deployments where there's no old record to expire, TTL doesn't matter much for the initial setup. Start at 300 seconds. Subdomains let you host multiple services under one domain. They're created as separate DNS records and can point to different servers or services. Common subdomain patterns: a pi.myap.com, your API server, or a separate API service www.myap.com, often same server as root domain admin.myap.com, admin panel staging.myap.com, staging environment, same or different server, cdn.myap.com, cdn or static file server. Creating a subdomain, add an A record with the subdomain as the name. For api.myapp.com, record type A, name API, value, IP of your API server. Multiple subdomains on the same server, you can have myapp.com, www.myapp.com, api.myapp.com, and admin.myapp.com all pointing to the same server IP. Jinx handles routing between them using server_name in separate server blocks. Wildcard DNS, star.myapp.com one IP. This makes every possible subdomain resolve to the same IP. Useful if you generate subdomains dynamically, like a SaaS platform where each user gets username.myapp.com. Wildcard record, record type A, name asterisk, value, your server IP. Name for subdomains to other services, you might want docs.myapp.com to point to your GitHub pages or Netlify site. Username, docsyourproject.github.io. Subdomain isolation is a security consideration. If you can separate services to different subdomains, a compromise of one subdomain doesn't automatically compromise others. Cloudflare is the most popular DNS provider for good reason. Beyond DNS, it provides DDoS protection, CDN, SSL termination, and security features, all for free on the starter plan. Setting up Cloudflare for your domain, go to cloudflare.com, add your domain, follow the setup wizard. Cloudflare scans your existing DNS records and imports them. You then update the nameservers at your registrar to Cloudflare's nameservers. This takes up to 48 hours for the registrar change to propagate. The Cloudflare proxy, Orange Cloud. When you enable the Cloudflare proxy on a DNS record, traffic goes through Cloudflare's network before reaching your server. Your server's real IP is hidden. Users connect to Cloudflare's IP, which proxies to your server. Benefits of the proxy: DDoS protection, web application firewall, caching, automatic HTTPS with Cloudflare's SSL certificate. Your server gets Cloudflare's IP in the request, not the user's IP. Handle this with the CF connecting IP header or configure Jinx to trust Cloudflare's IP ranges. DNS only mode, Gray Cloud. The record is served as a plain DNS lookup to your server's IP. No proxy. Use this when the proxy would interfere with your setup, e.g., for custom SSL certificates, some mail records. For Let's Encrypt, you can get certificates with Cloudflare proxy active, but the DNS challenge method works better than the HTTP challenge when proxied. Or switch to DNS only temporarily for certificate issuance. Cloudflare's free plan includes unlimited DNS queries, DDoS protection, basic WAF, and SSL. A reference of the DNS mistakes that cost the most time. Mistake 1: forgetting the @ symbol for the root domain. When you want myapp.com to point to your IP, the name field should be @ meaning the root. Some panels accept leaving it blank. If you put myapp.com in the name field, you create myapp.com.myapp.com. Mistake 2: not waiting for TTL expiry. You changed the DNS record but the old IP is still resolving. Check the TTL of the old record, that's how long you need to wait for the world to see the new record. Mistake 3: checking DNS from your local machine with a cached old record. Use an online DNS checker like whatsmydns.net to see what DNS resolvers worldwide are seeing, bypassing your local cache. Mistake 4: wrong record type. You created a name for the root domain. Most DNS providers don't allow name at the root, it conflicts with SOA and MX records. Use an A record or alias / a name record for the root domain. Mistake 5: updating the wrong DNS panel. You have records in your registrar's DNS panel, but you've also pointed nameservers to Cloudflare. Changes at the registrar don't take effect because Cloudflare is authoritative. Always update the DNS provider whose nameservers are active. Mistake 6: mixing up A and name. Name values are hostnames, not IP addresses. If you put an IP address in a name record, it won't work correctly. Mistake 7: forgetting to configure Jinx server_name. Even with perfect DNS, if Jinx doesn't have server_name myapp.com, Jinx won't know to serve traffic for that domain. A scenario about DNS resolution and propagation. You update your record from old IP 1.2.3.4 to new IP 5.6.7.8. The old record had a TTL of 86,400, 24 hours. You updated the record 2 hours ago. Your colleague in Germany reports they still see the old website at 1.2.3.4. You check from your machine and it works correctly with 5.6.7.8. Which of these best explains the situation? Option A: your DNS change didn't work, the record still has the old IP globally. Incorrect. You can reach the new server from your machine. The change worked. But not everywhere. Option B: your colleague's DNS resolver cached the old record before your update and it won't expire for up to another 22 hours because the TTL was 86,400 seconds. This is the correct explanation. DNS resolvers cache records for up to TTL seconds. Your colleague's resolver cached the record before the update. With a 24-hour TTL, that cache won't expire for up to 24 hours from when they last queried it, which could be up to 22 more hours. Option C, Germany has a different DNS root server that hasn't propagated the change yet. Root servers don't store records, they only store delegation information, NS records. Your record propagation is a matter of TTL expiry, not root server sync. Option D, Cloudflare is caching the old response. If you're using Cloudflare DNS-only mode, Cloudflare is authoritative and would serve the new record immediately. If your colleague's resolver has cached the old record, that's between the resolver and TTL expiry. The answer is B. This is exactly why you should lower TTL before planned server migrations to minimize how long clients are stuck with stale cached records.